Chapter 11, Equilibrium and Elasticity. Samples. Sample 1. A uniform smooth rod AB of length L and mass M rests at equilibrium in a smooth semi-spherical ball of radius r, where half L is larger than L, smaller than 2L. This condition means when you put inside, always have something outside the semi-spherical ball. If theta is the angle of equilibrium and P is the force exerted by the edge of the ball on the rod, show that P equal Lmg over 4r. B. Cosine 2 theta over cosine theta equals L over 4r. This is a question of equilibrium. Okay. Sigma F equal to 0 and sigma tau equal to 0. Let's first see how many forces acting on this rod. We can see this gravitational force mg and the normal force from the ball to the rod P. There is another force acting on this rod from the ball, okay? Because it's smooth, so there's no component along tangent. It must along the radial direction, okay? We try to avoid this force, so we'll pick up A as our reference point to calculate the torque, okay? And we see the torque at point A, mg torque. We can load this one. This is the perpendicular to this horizontal. This is this one. What is this one? This one, you see that this half L cosine this angle, and this angle is theta because this is horizontal. So mg half L cosine theta. This is clockwise. And this P around A is counterclockwise. They must be equal in magnitude and opposite in direction. So mg half L cosine theta equal to P. What is what? This angle. This perpendicular. This is from this rectangular triangle because this diameter of this ball. So this is equal to 2r cosine theta. Now let's see the second question around O. We still avoid the force here. Around O, this gravitational force torque around O equal to mg, this one, right? What is this one? It's very complicated. Let's make a reference line perpendicular. This heavy line equal to this line minus small this line. And this line equal to this line, half L cosine theta. And the small line, you look at it, this is a rectangular triangle. This angle is 2 theta. Why? Because this R, okay? So this theta, this is theta. This is a 2 theta, okay? Equal to sum of these two. So this small line equal to R cosine 2 theta. So let's see this one, mg. mg half L cosine theta minus R cosine 2 theta. P is very simple. Look at this, P is perpendicular. In this triangle, we'll find this length is equal to R cosine theta. From this equation, we can find the P. We put the P inside, and we can get the answer for the second part, B. That's it. Second example. A uniform rod AB, this is AB, of mass m and the length L is suspended by light inextensible string PA and QB. Length PA is L1, length QB is L2, respectively from the 2 points. And PQ is parallel horizontally, okay, and the distance is 2L. A force acting on A, vertically downward, is applied to a rod, so make it AB is horizontal, parallel to PQ. Show that F equal to mg L2 square minus L1 square over L1 square plus big L square minus L2 square. This is a equilibrium problem, okay? Before we saw the physics, let's study the trigonometry, okay? It's given PA is L1, QB is L2, L2 is larger than N1. And we see that PQ is horizontal, AB is horizontal. So PQ parallel AB. And then PQ is 2L, AB is L. So we find what? So we find in this big triangle, A and B should be the midpoints of this line. So points A and B are midpoints of PO and QO. In other words, AO equal to PA equal to L1, and BO equal to QB equal to L2. Okay? So this is L1, this is L2. Once we got this one, we go up. Now let's go to the physics. What we want to find is F. What we're given is this is the rod. So similarly, we have to use the sigma F equal to 0 or sigma tau equal to 0. In this case, there's 4 forces acting on this AB. T1, T2, F, and mg. We don't know T1 and T2. So we try to avoid these two as much as possible. What we do, we extend PA and QB. They intersect at point O. You see, all the force sigma tau around O must be 0 because AB is in equilibrium. And then in this case, we're trying to avoid T1 and T0 because around point O, their torque is 0. R is 0. So we can avoid T1 and T2. Then we write the equation around O. F torque around O is Fx. This is this direction, counterclock direction. Mg torque around O is this direction, is clockwise direction. They must be equal in magnitude, okay? Then we say Fx equal to mg, this one. This one is half L minus x. So we find F equal to half L minus x over x. If we find x, we can find F. How we find x? This is trigonometry. You see, this is the horizontal, this is the vertical. So x squared in this rectangular triangle equal to L1 square AO square minus this one. This square in this rectangular triangle equal to BO square minus L minus x square. We put L1, L2 inside. Okay, this is BO, L2, LX. Okay, and we extend this one, L1 square minus L2 square, okay, minus L square minus 2LX plus x squared. And we extend this one, we find x squared can cancel out. Very easily we find x. Okay, x equal to L squared plus L2 squared minus L1 squared over 2L. Okay? And then we put this one inside. Put one X inside. We get what we want. That's it. That's it. This is a junior high school math, so I'm not going to do it.